final talk this morning will be Unstructured Sparsity Meets Tensor Cores, Lessons from Sparse Attention in MoE. And Aparna, Chandramowlishwaran will get started.
Good afternoon, everyone. I stand between you and lunch. It's a talk at 12, so I'll try not to put you to sleep. Thank you to the organizers for the invitation to be here. So the outline of my talk is try to introduce a little bit about unstructured sparsity in AI, specifically in two of the building blocks of transformers where they show up, and tell you a little bit about some of the lessons we learned in trying to exploit, try to speed up these or design algorithms, hardware efficient algorithms for these two building blocks. Okay, so let me first start with introducing the unstructured sparsity in attention and mixture of experts. So how many of you show of hands are familiar with attention and mixture of experts? Okay, some of you. So, I mean, I think all of us know at least transformers. So transformers are the driver of today's large language models. There's a lot of controversy on whether large language models is going to be the future, but at least transformers are here to stay for now. And attention is one of the core building blocks of transformers. So essentially what we're trying to compute is this computation where we have three inputs: query, key, and value, right? And we're trying to do this QK transpose, which is essentially a matrix multiplication, do some kind of a normalization on this in the softmax, and then multiply with another matrix. So you can think of this as essentially matrix multiply with some importance bias baked in. So instead of each token attending to all the other tokens, it selectively tries to attend to a subset of the tokens. That's essentially the idea of attention, right? Similar to how we think about attention, if you don't know. Okay. So what is sparse attention? So sparse attention is the same thing, except we also have this another matrix A, and this matrix A is what brings in the sparsity. So we can think of this as, in the case of sparse transformers, this is often called a mask, and your mask is typically is some structured mask. So in this case, if you look at this red token, it only attends to some of the tokens that are locally next to it. So we can use this kind of a sliding window pattern, which is a structured sparse pattern. But you could also have other sparse patterns that are dynamic. So instead of picking just sliding window, I could pick the top k scores, and you would end up with something that looks more like the matrix on the right. And this is also what graph attention looks like. So in the case of graph attention, your A matrix is essentially the adjacency of the graph, right? So you can think of each of these rows as nodes, and these are your neighbors. The non-zeros are the neighbors in your graph. So in this case, also your sparsity is irregular and unstructured. Okay, and for many real-world graphs, it's very highly sparse. The number of non-zeros is less than 0.1%. So these are 99.9% sparse matrices. Okay. Okay. So and it so happens that this the computational pattern in sparse attention in sparse transformer and graph transformer also show up in a bunch of other popular models. So here I'm showing you two more, which is an attention-based graph neural network, which is a different formulation. No need to worry about this for this talk. And also graph attention networks. So the question is, what do these have in common? What is the computational pattern? The first thing is they all compute this QK transpose. It looks a little bit different, but in the context of sparse attention, this ends up being sampled dense matrix multiplication. So your A matrix is dense, B is dense, but you're only sampling based on the sparsity pattern in your mask or your adjacency. Okay? And then once you've computed this QK transpose, like sample dense matrix multiplication, you do a softmax. This is the same as standard attention. But after you compute the softmax, then you do a sparse times dense matrix multiplication, right? So essentially in this B matrix, you access sparsely depending on the sparsity pattern A, and then you have a sparse dense matrix multiplication. Your output is dense. Okay, so we call this pattern essentially the 3S. So the question is, how do you actually design efficient algorithms for this 3S pattern? So that's one question. That's sparse attention. So let me now introduce mixture of experts very quickly. So essentially, mixture of experts is the other building block. The other building block of your transformer is this feed-forward network. Once you've optimized tension, the feed-forward network tends to be the bottleneck in your transformer building block. And the sparsely gated mixture of experts was essentially a way to increase the number of total parameters in your model without increasing the flops proportionately. Okay? So what does it look like? So essentially, you take your feed-forward network, is usually implemented like a multi-layer perceptron, a dense operation. And you replace it with something that looks like this. So you have a router, and the router takes each token and then computes some kind of a score and routes each token only to the experts. I'll come back in a second to what these experts are, who have the highest scores. Okay? So in this example, this token gets routed to expert 2, expert 3, and expert n. Okay? So you can imagine that now the flops only scale with the number of active experts, not the total number of experts. So you could have a lot of these experts, right? But if you activate only a fraction of them, then you get a lot of parameters. You can scale your parameters without scaling your compute. Okay, and that is the idea. And this experts can be implemented using the same way we used to implement feed-forward networks before, using smaller MLPs. Or you could implement them, like today they are more popularly implemented using what is known as this gated linear unit, which it looks a little bit more complicated, a bunch of matrix multiplication with some activation. Okay? And beyond efficient scaling, another reason to have a large number of experts is lifelong learning. So recently a paper came out called Artificial General Intelligence and where GPT-4 and 5 are, and looking at different metrics. And one of the metrics that most of the models today are failing is lifelong memory, this catastrophic forgetting every time you leave the context window. And MoEs can help with that problem. And it's emerged as also a promising approach for lifelong learning, besides just scaling. Okay. So where is the sparsity in mixture of experts? So here I'm showing you the router distribution for two open source large models. This is OLMoE. The total number of parameters is 7 billion, out of which 1 billion is activated per token. And this is Qwen3, which is another very large model. And this is a 30 billion parameter model, of which 3 billion are activated. Okay? So in OLMoE, we have about 16 layers and 64 experts. And in Qwen, this is about 48 layers and 128 experts. And you can see here that the routing distribution is quite sparse, right? And there's a phenomena in MoEs, mixture of experts, called expert collapse, which happens during training. So where during training, the router tends to prioritize one expert. So all of the tokens end up going to like a single expert. So one way this is usually mitigated during training is to add a loss, a balance loss, which tries to balance the routing among all the different experts. So despite having this auxiliary additional loss, we see this skew during inference. So this is on a wiki text, and these models are open source on Hugging Face. Okay, so we see that some experts receive, you can see in this case, where there are some experts receive, for example, if I look at this layer, like less than 1% of the total tokens. Okay, So this is the sparsity, and we are talking about millions of experts. A paper came out last year from Google DeepMind where they're trying to scale this number of experts to essentially million experts, right? So here we're talking about like sparsity is only going to get more unstructured in that scale. Okay, so now that I've hopefully convinced you there's a lot of sparsity in these two building blocks, let me tell you some of the lessons that we learned trying to design hardware-efficient algorithms for these two problems. Okay. So before that, I just need to very quickly, in one slide, thanks to all the speakers who came before me this morning, I've already introduced tensor cores and GPUs, and so I won't talk about all of that. All I want to point out is that if you look at the GPUs today, most of the flops are coming from tensor cores, right? So the peak of the machine, if I look at it, in Volta it was 125 teraflops. With Blackwell, we have 4.5 petaflops. This is from a single GPU card. So if you don't use tensor cores, if your algorithm doesn't use tensor cores, you're essentially leaving most of the performance on the table. Okay? And there's an inherent mismatch between tensor cores and sparsity, right? Because these are meant to run dense matrix multiplication, and we have all these sparse problems. So this is the challenge. Yeah, question?
2 by 2 dense matrix multiplication is a scalar, essentially. So how big are the matrices that the big fat tensor core on the right needs to operate?
Great question. That's here. So, so tensor cores expect that your matrices have to be a certain shape, and the operands have to be a certain size. And this also varies depending on the precision that you're operating on. So another trend that we've been seeing is that from Volta to Blackwell, NVIDIA has been trying to go lower and lower in precision. Now we have like micro precision, like FP4. So depending on the precision, but these matrices tend to be pretty small, right? So if I take even, like, let's take BF16, this is, if you're trying to multiply two matrices, A and B, size A is M by K, K by N, the resulting matrix is M by N. Your M and K can have very small dimensions. It's like 830 to 16, not very large.
Well, I can't read it from here.
So the matrices M is like, to take one example, it can be like eight rows of M, or 8 elements of M, 32 of N, 16 of K. So pretty small. Yeah. So your data has to be in this format to be able to also run on these tensor cores. Right? So they're not designed for random sparsity. So the first lesson is that sparsity must be structured to be accelerated on tensor cores. Right? And we see this in both hardware and software. So hardware, NVIDIA also came up with this sparse tensor cores, where they try to enforce this 2-4 sparsity, meaning that if you look at the 4 elements here in this first row, 2 of the elements are non-zeros and 2 are zeros. So you have, that is the 2-4 sparsity. So any 4 consecutive values, 2 are sparse, 2 are non-zeros, 2 are not non-zeros, right? So they came up with these kind of sparse tensor cores. So you can do some sparse operations on GPUs, but this is also structured sparsity. And this has been exploited a lot in pruning, these weight matrices where you can prune them to fit in this pattern. But this doesn't really work for graph problems, right? Where your sparsity is a lot more unstructured. If I'm doing top K, I can't expect my top K to fit in this 2-4 sparsity format, right? And we also see this in the software because dense attention scales as order n squared, n is the number of, n is the sequence length. The community has come up with a lot of different sparse masks, but again, you see all these sparse masks are structured, right? So somehow the key to performance is enforcing some local structure. So what does this mean for unstructured sparsity, for graph problems? So if you have some sparsity like this, what do? What we ended up doing is try to make the unstructured sparsity look structured. And what do I mean by that? Is there's been a bunch of different sparse formats that have been designed for tensor cores in the last some years. And they all go something like this. So let's take our this matrix. First, what we're going to do is divide this matrix. We're going to block this matrix into row blocks. Let's call this block of rows, this red floor blocks of rows, has a row window. Okay. And if you look at each row window, within each row window, we can see there's a lot of fully zero columns. Okay, somehow you can get rid of the zero columns and take all these zero columns and remove them. So we end up with a compressed matrix that looks something like this. Okay, and the way we choose the blocking size is the row window size. And again, once you've got the compressed format, you can further block each row window into these 2D blocks. Call this a tensor core block. And the way we choose the size of the tensor core block is based on the operand sizes that I showed before, because this is what will eventually run on the tensor core. Okay? And the different methods that I showed earlier, the way they differ is mainly in how they how they store this compressed format. I'm going to give you an example of one, which is the binary sparse block that we developed. And we have to keep track of three things here. So we have to keep track of the number of tensor core blocks in each row window. So in the first row window, we have 4. So we have to keep track of this row offset. And since we're doing this compaction, we need to know where the non-zeros are. So we need to know this column in the compacted representation corresponds to which row in the original sparse matrix. So we have to keep track of this column sparse to dense mapping. So in this example, this first column corresponds to column number 1 in the original matrix. The next corresponds to 4, and so on. And the third thing we have to keep, yes, question.
Permute the rows so that your compaction is better, but whatever.
Yeah, so that's been a lot of work. So here, Aiden has done a lot of work on row reordering to make this, to exploit locality in the sparse matrix, do kinds of different row reordering, tons of different heuristics on how to do that. So yeah, we know how to do that. So assume that you do that row reordering and then you do this on top of that. And then we need to know where the non-zeros are. So for our problem, we don't care about the value of the non-zeros. We only need to know whether a certain location has a non-zero or not. So we can store this efficiently using a binary bitmap. Okay. So once we have this, then we can do this computation where we assume that each of these blocks, we treat them as dense. They run on the tensor core. Okay? And if you do this row reordering and do kind of blocking efficiently, we can make sure that we increase the density of this as much as possible. Okay. So now let me switch to mixture of experts. So what do I mean by we have to make sparsity look structured and mixture of experts? So this is the mixture of experts diagram from earlier. So a simple way to implement MoEs is essentially to just loop over all the experts. You can have a for loop go over all the experts, and then you can compute each expert, gather all the tokens for that expert, do the glue computation, and then write back. And this is, I don't know if you believe me, but this is how Hugging Face implements MoEs today. Like if you go look at Hugging Face, this is how they implement MoEs. But when we're talking about fine-grained MoEs, right, we're talking about 128 experts or 1 million experts, the computation, especially when you have this high skew, the number of tokens in each expert can be highly varied. You can have very, very small computation gems to compute that will not saturate your GPUs. So your GPU utilization is extremely low when you do this on small gems. This is okay if you're doing something like Mistral, where you have like 8 experts and you activate 2. Or the Google's G-Shard, you activate 1 or 2. But it doesn't work when you have fine-grained experts. So a smarter way to do this is to make your computation look more structured and use primitives like group gem. So group gem is something that was introduced. I think it's now part of most of the libraries, like Cutlass, Kublas, even Triton implement group gem. It's a variation of the batch gem, if you know about it. So you have a number of different matrix multiply. If they're all the same size, you can use batch gem. Group gem is if the matrices are of different sizes. Question?
These trained LLMs are used in 2 different ways. They're trained and then they're used in inference.
Yes.
Those situations are very different. In training, throughput is what matters.
Mm-hmm.
Inference, latency is a big deal. So you haven't said whether these optimizations are for one, the other, both? Do they work equally well?
So right now we're just talking about, it applies to both training and inference. We're just talking about how do you actually realize this computation, right? So I agree, during inference you don't do some of these things, like when you're training, you train with all these auxiliary laws, and you have a bunch of different things that you throw away when you do inference. But the fundamental algorithm usually is relatively similar in training and inference. Okay, so the way you do this is for each token, the router assigns weights to each expert, and the top k are selected. And you do a group operation or a gather, where you gather all the tokens that are assigned to each expert. Okay, so now you have a structured computation. And then you have a bunch of different gems, matrix multiplies. These are all of different sizes. Then you can call the group gem API, or the group gem call from any of these libraries, which are highly optimized backed by backend expert developers who write these hand-optimized kernels. And then you have to scatter the output back to the original layout and then do a weighted sum, because you have these scores, so you have to weight your output by the scores and then sum them up. Okay, so this is a more efficient way of doing this, and the reason for doing this is so you can use this efficient batch gem or group gem APIs. So again here, to accelerate this computation, what you have to do is you have to do this gather. Right? You have to do this group operation. So again, MoE, the sparsity must be structured, so you can actually accelerate it using these custom libraries. Okay, so that is my first lesson. Second kind of false off it is that these individually optimized kernels, they don't compose efficiently. So let me give you an example with attention again, and this applies to both dense and sparse. So if you had to do this naively, how would we do this? By naively, I mean you still nobody wants to go and write sample dense matrix multiplication or SPMM. I think Aiden has already done a lot of this work for us, and Sadai too. So we just want to use these optimized functions, right? People have already written. So as the first attempt, that's what you would go do. You go use these optimized kernels that's already been written. So I would load Q and K, compute STDMM using Aiden's optimized kernel, and then write it back, and then load S again, do a row-wise softmax using, again, an efficient bandwidth optimal kernel, write the output back, load PV again, do the SPMM. You know how to do SPMM, we've been doing this for a long time, and then write it back. This is terrible for the entire kernel, because you're doing all of these are intermediate operations. So all we care about is QK, V, and then output, right? All these S, P, these are all intermediate operations. You're doing all these data movement. Sadai talked about data movement. Data movement is the killer. This is not efficient at all. So, but this is how we started writing these kernels. So there is very efficient fused kernels for dense attention. The most popular one is flash attention, which is very well known. It's used by, I think, most of the well-known libraries, including PyTorch. But what about 3S that shows up in sparse attention? So we saw that a lot of people were working on kernels for tensor cores, and even one for sparse tensor cores. But nobody was trying to fuse these kernels. They're all trying to optimize individual kernels and make them fast using all these different techniques like reordering, all of these optimizations. But they were not optimizing the entire computation. They were optimizing individual kernels. And this is a problem. And so that was one of our contributions, is try to design an algorithm specifically for tensor cores for sparse attention that also tries to be I/O aware, try to combine. People have tried to do fusion before, but nobody tries to use it for tensor cores. And I can mention, if you don't use tensor cores, why are you using the GPU? Okay, so now let me tell you a little bit about how we actually do this. So there are two ways of parallelizing this computation, right, and fusing this operation. So one is you can do node parallel. By node parallel, I mean that each of these rows, and thinking of this as a node, you give this to one core or tensor or thread block. Right? Or you can do edge parallel, where you divide up this S matrix evenly among the different thread blocks, so everyone has load balanced work. So if you are using STDMM, right, sample dense matrix multiplication, this is the most efficient way to do this. right? This is load balance. This is the most efficient way. But this is not optimal for doing softmax because softmax has to do a row-wise normalization. And I need data from 2 different thread blocks, which means I have to go to global memory. Or I need to move to a more richer university where I have access to Hopper and Blackwell, right? So, and if you're using SPMM, then node parallel is the more natural way of implementing it. So there's a tension between what is optimal for one algorithm is not optimal for the other. So when you're doing fusion, you have to think about, okay, what is optimal for the composition of these kernels? And since our goal is to have a fully on-chip fused algorithm, we go with node parallel where there's no synchronization. So each of the colors means that operations computed by completely independent cores, so to speak. And there is no synchronization among them. But what is the downside is that you have this irregular load balance, imbalance that you have to handle at the scheduling time. Okay. So I won't go into the full algorithm, but this is kind of the fused algorithm. And as you can see, there's essentially, this is the computation that is, the entire kernel just fits in one slide. Right? And all the 3 operations, SCDMM, softmax, and SPMM, are fused into a single kernel. And we have to do something a little bit fancy to handle the softmax, but this is not something that we did. It's already been done in the context of dense attention, where you have to do an online softmax to be able to do softmax on blocks, on tiles. Okay, and within each, the computation is run on the Tensor core using a Tensor core gem. And again, we have a way of breaking down the computation among the different warps in such a way that each of these colors correspond to computation that's done by different warp, and they're all computing independently without any synchronization among them. So this is as parallel and has reduced synchronization as we could design this kernel. Okay. So show you some results on a bunch of different graphs. Show you results on 2 types of graphs that essentially show up. These are the classical full graphs, right? You have a single graph, you have connectivity among them. And these are batch graphs, so a batch of smaller graphs. And these show up a lot in science applications, like in chemistry. This is actually a protein data set, PPA, and code 2 is the abstract syntax tree of many different programs. So these tend to be not single large graphs, but a batch of small graphs. So kind of tested this on both of these types of data sets. And here is some performance. So the only takeaway is that we do very well, much better than the other state-of-the-art. The only time is this yellow bar, this orange bar, which is higher in some cases. But that's because they use a different version of softmax that's not stable. It's like a naive softmax. What you want to really use is a max stabilized softmax, which is stable. So when you do use that, then we are faster than all the other implementations in all cases, and especially for the batch graphs. And this is not even the best we can do. So, let's see. Okay. So, So what about mixture of experts? So what is often overlooked with MoE efficiency is that at fine-grained scales, it's not just a matter of expert compute, right? Routing, where after you route, you gather all these tokens, and then you scatter the tokens back, and then do a weighted sum, which is essentially a reduce. These are irregular operations, and they are bandwidth bound. Okay? And when you have a lot of different experts, they tend to dominate the overall running time. Okay? So how do you, again, use this idea of fusion here? So what we essentially did is we tried to fuse the gather-scatter with the expert compute. And if here you look at expert compute, it's a little bit more complicated than a simple MLP. You actually have 3 group gem. You have the matrix multiply. This is a group gem. It's another group gem. You have an activation, and then another group gem. Okay. So here are some results on the OLM, MoE, and Quen models. So this is just a benchmark showing what happens when you try to fuse gather and scatter with the group gem. And perfect means that all the experts have the same number of tokens routed to them. Balanced means They have different number of tokens routed to them, but they are somewhat balanced. Skewed is when it's completely skewed. Some experts have a lot of tokens, and the other experts have very few tokens. So in all of these different routing distributions, the takeaway here is that we can very efficiently fuse gather and scatter with group gem. So that does not affect performance, but what does affect performance is a routing distribution. So if you're highly skewed, you do see a difference in performance. So the routing distribution affects performance. The fusion is pretty efficient. So here again, you should remind the OLMOE has like 64 experts and Qwen 3 has 128 experts. And here's the performance end-to-end for inference. This is not for training. We do have also the backward pass, but I'm not showing the results here. This is just for inference. And here on x-axis, we have increasing number of tokens, and y-axis is the time. So the fused MoE is fusing the gather scatter with expert compute, and the torch grouped is the unfused implementation from PyTorch, which on the under the hood calls CUDNN group gem to do the group gem operation. Okay, and our kernel is actually written in Triton, so we actually try to use all of the Triton's compiler magic also in the back end, although I don't think it's helping. But that's for another story. So the third, I'll go very fast after a few slides. So let's go very fast. The third lesson is that the data layout has to align between your data access from your memory to your on-chip cache and your compute schedule. So here is a computation just for STDMM that runs on one tensor core. So each tensor core is executed by one warp. So a warp has 32 threads. And this is the layout that your tensor core API expects your data to be laid out in. Okay? But this is not good for coalescing and data reads. Because if you look at this, each thread in the warp is only loading 32 bytes of Q and 32 bytes of K. What we really want to do is to do coalesce 128 byte loads. But there's a mismatch between what tensor core expects and how the data is actually accessed. So the one way we actually address this is to do a permutation of the rows of Q and K. So you can essentially permute Q and K and such that essentially permutation of the rows. And you end up with this layout where then now each thread can load 128 bytes coalesced. Okay? So some way to like trick. But the point here is not the optimization. The point here is this inherent mismatch when you're trying to use dense computation for a sparser problem. And for SPMM, we do something different where we permute the columns of V again. And the point of this slide is the darkest bar here is the optimization on top of everything else, which is doing the permute. And you can see that across the board, this is one optimization that always pays off, right? Because data movement is expensive, no matter what the graph problem is, no matter the sparsity of the problem. Data movement always is a problem and always helps. So the final lesson is the parallelism granularity must adapt to sparsity. So what do I mean by this? So here's a simple example to illustrate this lesson that we learned, and this is still an open problem. So let's say you have 3 gems here, and then you break this down into tiles. Okay, so gem 0 has 4 tiles, gem 1 has 6, and gem 2 has 6. They're different shapes. And you have 4 SMs. Think of these, if you don't know GPUs, as cores. You have 4 cores. And each core can essentially schedule 2 of these tiles. Okay? So what the group gem scheduler, we don't know what happens in CUDNN because it's closed source, but what happens in both Cutlass and Triton is that the group gem scheduler will try to schedule these tiles in this kind of a round-robin fashion. And this is great. You think at this, look at this, and this is awesome. It's very perfectly balanced. It's really nice. But what they also do is that you can tune. So Triton can tune for the block sizes, but it would pick a static block size, one block size for all of the gems. Okay? Now think about when I have 128 different experts, highly skewed, where the expert gems can go from very small to really large. The tile size that's optimal for one is not the tile size that's optimal for another. We're going to pick the same static tile size for all. So how do you actually do this? We end up padding. This is what happens today. And this is highly inefficient. So what we really need is adaptive tile sizes. But we can't do that today. And once you have adaptive tile sizes, how do you actually schedule them? You need some kind of a dynamic scheduler, right? So maybe that's a fifth lesson. One other trend is like what we're seeing is this persistent thread blocks, or persistent kernels. And I think that is a new load balancer, which is actually very bad for algorithm designers because the onus is again back on us to do the scheduling. So all of this leads me with my one slide conclusion. We need compilers. We need compilers that can jointly reason about sparsity, tiling, and memory hierarchies, so we don't have to do this. But that's not happening, so I'm still in the job market for a long time. So thank you for your time. And this is work mainly done by two of my PhD students, Zitong and Arthur. And one of the work is published, our sparse attention work, and the other I presented MoE is currently work in progress, so showed you some preliminary results. Thank you. Happy to take questions.
It's lunch.
Yeah, it's lunch, so you can always ask me questions.
Thank you very much.
Thank you.
And there was a reception at 3 o'clock, and then Bob Tarjan will be giving the lecture at 3:30.